Good morning and welcome to this presentation on AI-assisted counting of colony forming units. This project was a collaboration between GSK Vaccines and Radix. My name is Laurent and I'm CTO at Radix, and my co-author on this project is Paul Smith, who is Senior Manager of Data Science at GSK. So diving right in, this presentation has three sections. In the first section, we briefly describe who we are, what AI is exactly, and what AI can contribute to in the pharmaceutical sector. In the second section, we go into the development of the AI-assisted CFU counting solution. So that includes describing what the problem is, showing you what the solution is to that problem, and also talking a bit about the impact that this project has had at GSK. And in the final section, we explore what else AI could do for the pharmaceutical sector, where we believe that there are actually a lot of these low-risk but high-impact projects, such as CFU counting. So for those not familiar with GSK, GSK is a global healthcare company whose purpose is to help people to do more, feel better, and live longer. And they basically have three global businesses, namely pharmaceutical medicines, vaccines, and consumer healthcare products. Radix is an AI solution provider based in Brussels, in Belgium. And we started in 2018, quite a young company, and now have about 25 or so people working from Brussels. So what is artificial intelligence exactly? Well, AI to us is simply this idea that we can automate tasks that require some level of intelligence, for example, human intelligence. By itself, though, it is not a technology. And there are multiple technologies that can help you realize this concept of AI. Machine learning being the most commonly known one. And to substantiate that claim a little bit, here's a tweet from François Cholet, who's well known in the field of machine learning, more specifically deep learning. He authored one of the most popular deep learning libraries called Keras. And in this tweet, he writes, "Our field isn't quite artificial intelligence. It could maybe be better described as cognitive automation, so the encoding and operationalization of human-generated behaviors and skills, which is pretty much how we look at it as well." He does go on to say that the intelligence label is to him a category error. However, in our opinion, calling it artificial intelligence is more of a statement about where you want to end up, or what the ambition is in the fields, rather than what it is today. So as I mentioned, there are different technologies to help you realize artificial intelligence, the most well-known among which is machine learning. And machine learning is basically a class of technologies that allows you to realize AI through showing an algorithm many examples of the desired behavior. And over time, that algorithm learns to replicate the desired behavior. Within machine learning, there is a subclass of machine learning models called deep learning. And in deep learning, the idea is to use neural networks. Deep learning has been very popular in recent years, mainly because of its success in the fields of computer vision and natural language processing. There are, however, other technologies that can help you realize artificial intelligence. One of these is called operations research. And crucially, in operations research, you don't achieve AI by showing a model many examples of the desired behavior, but instead you describe what you want to achieve and then use an AI algorithm to help you search for that optimal solution under the conditions that you wrote. And that's actually why we call this a declarative form of AI. However, in this project, we'll be using deep learning, because deep learning is really well suited for this task that we're looking at, which is in the computer vision domain. So what could AI contribute to in the pharmaceutical sector? Well, if we look at the drug development process, we see two obvious problems. The first is that it takes years, potentially even decades, to develop a single drug. And the second is that the cost to develop these drugs is also enormous. So if anything, we hope that AI, or we do believe that AI can contribute to reducing the turnaround time and the costs required to develop these drugs. All right, so diving into the AI-assisted CFU counting. What was the goal exactly? Well, GSK approached us and told us about this step in the development of vaccines where a lab generates hundreds of images that look kind of like these. So these are images of petri dishes, and what you see on this image are bacterial colonies. And each circle that you see on the image is called a colony forming unit, or CFU. Now, as part of the vaccine development process, lab technicians have to annotate these images and identify these colony forming units as either virulent or avirulent. So that's what you see here on the screen. This is a human annotation of these CFUs. And the question that GSK asked us is, well, can this process be automated partially or completely through AI? And so that's what we helped them to investigate. So the way that we did that was we took 4 steps. In the first step, we had a discussion with them on how we should measure the impact of this project. Because if we know how to measure the impact, we can also optimize for maximum impact. So we spoke to the lab, and they clearly stated that these are the 2 goals for this project. The first goal is they wanted to reduce the amount of time, human time, necessary to annotate these images, to count the number of CFUs in these images. And the second goal is to also, if possible, increase the accuracy by which these CFUs are counted. Once we defined the goal, the next step was to understand the end user. Because if we don't understand the end user, we run the risk that this application won't be used in the end, or that it's not optimal for the actual usage, the intended actual usage. So we conducted some interviews with the lab technicians who would be using the solution, and we came to a number of interesting conclusions. The first is that users, or in this case, the lab technicians, don't find this task of counting CFUs very exciting. They have much more interesting, much more satisfying work to be done. So indeed, they would be quite happy if we could relieve them at least partially of this task. The second conclusion is that we found that users actually spend a lot of time on these peripheral tasks related to CFU counting. It's not just the counting of the CFUs that takes time. It's also, for example, getting the images onto the machine to be able to count the CFUs, and then also generating the reports that that is derived from those CFU counts. And finally, we learned that the lab technicians don't always agree on what the correct count is for a particular image. So we expected that that might make it challenging to train an AI to count these CFUs automatically, since there is not always a ground truth or a single version of the ground truth available for a particular image. So coming back to this picture, what we see here is that our goal for the AI that automates this task is to reduce the time required to count the CFUs, and hopefully also increase the accuracy. But as we mentioned, we see that there are these other opportunities now through these interviews to increase to decrease the amount of time required to do the counting and to report on these counts. For example, by automating the ingestion of the images, and also automating the generation of the reports that come out of this process. With that information in hand, the next thing we did was to get to work to build a first working version of the solution, which we designed intentionally as a skateboard solution, meaning that the goal was to develop a working version, a functional version of the application as quickly as possible, so that end users could open it up, interact with it, and give us feedback on what the next best steps would be to improve that solution. So after the first sprint, this was the first version of the application that the end users got to see. So what you see here is someone uploading an image of a petri dish, and in the background, the AI model is running to predict the different counts of the different types of CFUs. Users could open the image, look at the different colony forming units, switch their type, potentially remove them as well, zoom around and pan on the image, and that was it. And this was really valuable, we found, to be able to show the end users so that they could experience this application give feedback on what they believed to be the next best steps to improve this application, to make it more useful to them, to increase the impact even more. For those interested, here are some of the technologies we used to develop this first version. So the whole solution runs on Microsoft Azure's cloud platform on Docker images. The AI model itself was trained using TensorFlow, and the front-end application that you see here was built on top of a front-end framework called Vue.js. All right, once we had that first working solution, that skateboard solution, we took the next sprints to iterate on that solution multiple times until we arrived at a version of the application that end users were completely satisfied with. And that version looked like this. So here, a user is uploading images. The images are being processed in the background. You see the counts. You see now that the different colonies are now shown in an elliptical form instead of a rectangular form. There's a zoomed in portion of the screen where people can see the zoomed in version of the image. There's a side-by-side comparison. And the application is now also aware of the different dilution factors and replicates. And here you see the end user generating an Excel file of the results. Finally, we took some time at the end of the project to also measure the impact that this project has or could have at GSK. And the first thing that we did was to measure the time it took to model to count these CFUs, as well as the accuracy with which they are counted. So what you see here on the screen is the accuracy with which they are able to be counted. And happily, we were able to conclude that the AI model is able to achieve superhuman accuracy. Now, what does that mean exactly, superhuman accuracy? Well, in this case, that means that the number of CFUs that human experts disagree on in any given image is more if you look at the disagreement between human experts than if you compare with the disagreements with the AI models. So basically, humans disagree with each other more than they disagree with the AI model. So on the graph, what you see here is on the y-axis the number of CFUs that humans disagree with on any given image. And on the x-axis, you see for what type of CFUs the disagreement holds. So for example, for BVG minus CFUs, human experts disagree with each other on about 3 or so CFUs per image, while they disagree with the AI model on just over 2 CFUs per image. So this whole test was based on the annotation of 35 images by 2 lab technicians. In total, about 1,600 or so CFUs were annotated. We also found that the lab technicians took about 35 minutes on average to perform this task, whereas we expect that this could be reduced to about 5 minutes by relying on the AI itself. So that would be a 6-fold improvement in time. So what else could AI do for the pharma sector? Well, looking at the other opportunities within the drug development process, we find that there are actually quite a lot of other interesting candidates for automation and optimization. So the first one we already discussed in this presentation, which is CFU counting. Another really interesting one could be the automation, either partially or fully, of writing the reports that correspond to these statistical studies. So that could be done using a domain within AI called natural language processing. Also, document classification, so making sure that all of the documents that are created as part of this process are classified correctly. Is really important to be able to find those documents, and is also important with respect to the creation and submission of initial applications, which is a huge undertaking. And that's also something AI could support in the assembly, basically the creation of an initial application, to improve that process, to make that faster, to make it more accurate. And finally, we see another opportunity is to give lab technicians, statisticians access to a more intelligent search where they can ask questions and where answers to those questions could be formulated as snippets from the different documents within the whole documents warehouse. These are just a few potential applications that could help reduce the turnaround time, reduce the costs in the drug development process, but there are undoubtedly very many more to explore as well. So in conclusion, in the CFU counting proof of concepts, we estimated that the AI could save up to a factor of 6 on the workload of the lab technician. We found that the AI can achieve superhuman accuracy in the sense that human experts disagree less with the AI than they disagree with each other. And finally, just like CFU counting, we see that there are actually a lot of low risk but high impact opportunities beyond drug discovery itself. So with that, I want to thank you for your attention. And if you like, you can definitely go ahead and visit us at either radix.ai or gsk.com. Thanks a lot.